Manure happens. The consequences of feeding some 7 billion humans. Not that all 7 billion are carnivores or omnivores. There are probably about 300 million vegetarians in India and maybe a couple hundred more throughout the rest of the world. But the vast majority of people are omnivores. And as development continues throughout the world, more and more people want to aspire to that standard of living that includes meat in their diet. This is just to give a very broad brush view of the global nitrogen cycle. To emphasize, obviously there are many more boxes and arrows that could be added to this, but the point is here is to emphasize how important fertilizer inputs are, and also agricultural biological nitrogen fixation into the global nitrogen budget. We have more than doubled the amount of reactive nitrogen entering into the terrestrial biosphere, and if you include the oceans, we have doubled reactive nitrogen in the biosphere. Now, that seems to resonate when I talk to biogeochemists and some other scientists, but when I present this sort of thing to a policy group or to non-scientists, you know, the eyes kind of glaze over. I mean, what are teragrams of nitrogen anyway? By the way, that is 10 to the 12th grams of nitrogen is a teragram. And so what are the consequences of that? It was actually this paper that was published in Nature in 2009 that I think really caught the imagination of much of the policy community, the non-scientific community. Actually, I think it's a really lousy figure. You kind of have to stand on your head to read it. And to me, there's no relationship between, you know, these red triangles and where they occur on the globe. But nevertheless, even though it may not have been the greatest graphic in the world, and also, by the way, this was not a peer-reviewed paper. It's since been updated with a peer-reviewed paper. But it has captured the imagination and put nitrogen on the policy map, so to speak, by indicating that this notion of a planetary boundary, that's something that the non-scientific community can wrap its head around to some extent, that there are limits to how much we can perturbate the global system, and that we've already caused extinction of many species, and so in terms of biodiversity, it indicates that we're already above the planetary boundary, and in terms of climate change, we're well along the way to being committed to more than a 2-degree change in climate. But this was a new one for a lot of people, that from this analysis and subsequent updates, that we've already exceeded a planetary boundary of nitrogen. And as a consequence, there's much more interest in this topic in the policy community, which is encouraging. Actually, I want to back up a moment and mention that there is some input of nitrogen through combustion. But fortunately, this is one area where, at least in the developed world, we've made a lot of progress. Now, if you read the New York Times today, you can see that that's not true across the world, that India is facing incredible smog pollution now that has to do with a combination of burning agricultural residues and combustion. But inputs from the atmosphere, at least in the United States and Western Europe, have come down tremendously in the last 20 to 30 years. In the US, with the enactment of the Clean Air Act and its amendment in the 1990s, that was at a time when bipartisan agreement on these sorts of things could be reached. And this is a slide from a colleague of mine at the Appalachian Lab, Keith Eschliman, where he has been measuring since that time nitrogen both in wet deposition and also nitrogen concentration in the headwaters of the Potomac River. And both have been declining over time. And that is a direct result of the Clean Air Act And when we look at progress at the Chesapeake Bay, this conclusion of his is rather controversial, by the way. There are some who would say that no, what progress has been made in the Chesapeake Bay is also attributable in part to changes in agriculture. But it's hard to actually prove that, that improvements in best management practices in agriculture have really made a difference yet. There's likely to be a long lag time between those changes and the time that we actually see changes in groundwater entering the Chesapeake Bay. But we can tell that loading through the rivers has declined, and that is largely due to either sewage treatment or this example of reduced nitrogen deposition. But the other part, the bigger perturbation, is the agricultural system, the system that we need to feed the world's growing population and to nourish them better than they've been nourished in the past. And that is an inherently leaky system. We will never get a food production system that has no leaks of nitrogen because living systems are just not 100% efficient. And this diagram is sort of a metaphor of nitrogen flowing through a leaky pipe. The first pipe being our crop production system, and much of that food that's produced is actually fed to animals rather than to humans. In fact, more than half of the crops are fed to animals. And if you consider the inputs on whether it's kilograms per hectare or pounds per acre or whatever units in terms of application of synthetic fertilizers, on average, by the time it gets through the first pipe, and for those crops that are consumed directly by humans, only about 14 in 100 units actually end up in the human mouth. The rest goes into the biosphere. And it's worse if we were eating animal products that only about 4% of the nitrogen inputs are actually consumed by humans. Where does the rest of it go? Well, it all goes out these holes in the pipe, either into the atmosphere in these forms of ammonia, nitrous oxide, nitrogen oxides, or dinitrogen gas, which is the only innocuous one of these, or it leaches out into groundwater and surface waters in forms of ammonium nitrate, dissolved organic nitrogen, or particulate nitrogen. Well, this process of producing fertilizer to use on our agriculture has been a great boon to human health. We are on this planet better nourished than at any time in human history. It's not to say it's evenly distributed. There are still about 800 million people in the world who are malnourished. But on average, we are better nourished than at any time before. Sometimes you can overdo it. And in fact, while there are about 800 million people who are undernourished, there's about an equal number who are overnourished and who have significant health problems, diabetes and heart problems because of being overnourished. So it goes both ways. And just as people can be overnourished, likewise ecosystems can be overnourished. Now, when I give this talk, I often give an example of each one of these. I'm going to presume for this audience I don't need to, particularly for the first item on this, the bullet item, that you know a whole lot more than I do to the extent to which nutrients contribute to eutrophication, dead zones, and harmful algal blooms. I think most of you are probably aware that nitrate is regulated in drinking water. Perhaps some of you are less aware that nitrogen oxides form ozone in the troposphere and also PM 2.5. That's 2.5 micron sized particles that are inhaled deep into the lungs. So those are also regulated by EPA. Nitrous oxide is a potent greenhouse gas, the third most important greenhouse gas in terms of radiative forcing. It also contributes to stratospheric ozone depletion. That's the good ozone up in the top of the atmosphere. And I've already mentioned nitrogen deposition. One of those impacts of nitrogen deposition, including in addition to water quality, is also a change in biodiversity of both terrestrial and aquatic animals and plants. Now, if I had a poster board like this out in a cornfield, And I think this statement, I don't know about the exact numbers, but the statement is roughly true, that the reason that all of us can be here and in endeavoring in academic and intellectual processes is that we don't have to go out and till the fields to get our own food. But on the other hand, if I could add a slogan to this, and thanks to PowerPoint I can, what I would say is what we really need is, let me see if I can advance it, more food and low pollution. It's easy to remember, mo, fo, lo, po. And the question is, how can we do that? Well, here's an extreme example of the very high-tech approach in agriculture, where tractors like this have sensors that can detect because of the reflectance of the light off the crop, can make estimates of the amount of nitrogen in the crop, and therefore determine how much ought to be added out the back of the tractor as it's moving along the field. And so this is called precision agriculture, where we're using high-tech approaches to try to match the amount of fertilizer needed at the right spot at the right time. And experiments that have been done at agricultural stations, well, actually on-farm research with cooperating farmers, show that with this approach, the amount of fertilizer that was used was about, I don't know, 25% less than the amount that the grower would have used otherwise based on state agricultural recommendations of how many pounds per acre one ought to apply normally. And the yield, sorry for the American units here, but that's the way American agriculture works, in bushels per acre. I don't know if that's per fortnight or how often, but anyway, that you get about the same yield, and this is an index of partial factor productivity, it's just jargon, an index indicating nitrogen use efficiency. And we're going to be talking later about another form of nitrogen use efficiency. Well, that's the high-tech approach, but the question is, why aren't farmers adopting more of these approaches? And there are a whole bunch of others that I'll mention very briefly in a moment that are much lower tech. And so the question is not so much just the technology or just the science. What we're learning is that we have to include the social science and the economics. This is a survey that was done by a colleague at Purdue University, where farmers get their most trusted information. And the light, or the green bars up here indicate, I can barely read there, I can see it down here. The strong influence. And so really the places they get most of their information is from other family members, from the fertilizer salespeople, from the seed salespeople, from private consultants. And I'm sorry to say that University Extension is way down here, even below lawyers and bankers in terms of trusted sources, and that's pretty low. So we really have to think about, if farmers are going to adopt something, if they're going to do something different than Dad and Grandpa did, and I'm sorry, most of the farmers are male. Interestingly, a lot of the landowners are female and rent out their land, but the actual practicing farmers generally are male. And to get information to them, we have to think about new strategies. And what's happening now is that many private consultants, and even the people that work for the fertilizer industries and the seed industries, are becoming certified. And there are, for instance, the Soil Science Society of America, Agronomy Society of America have certification processes. And so a way to get information from Ag Extension to the farmer is to go through these certified consultants. Now you might ask, isn't there a conflict of interest? Aren't they going to sell me fertilizer I don't really need? Well, you could say the same about the person that does your auto mechanics for you. Are they going to sell you a brake job you don't need? Is your dentist going to sell you a bridge that you don't need? Or if you have a trusted relationship, perhaps it can work, that this will be a trusted source of information. And more they're selling information in addition to selling products. What sort of programs, conservation programs, does this farmer qualify for? What sort of tax advantages can be gained or penalties averted by adopting certain practices. And so they're selling a suite of products and information. So that's the way things are moving at the moment. And in fact, this is a slide from an association of fertilizer industries, suggesting that when we consider productivity of the yield and so forth that are normally thought of, we must also consider the environmental and socioeconomic processes. And so they are promoting to farmers throughout the world now this thing of 4 R's. It's not the 3 R's that we learned about read and write and arithmetic. Instead, it's the applying the right source, the right rate, the right time, and the right place. This is a very American approach. It's non-regulatory. You can bet there are not 5 R's that add the right regulation. And in Europe, they're doing things a little bit differently. But it's trying to get farmers on board to see that this is in their best interest. So just quickly, some of those examples are slow-release fertilizers, nitrification inhibitors, making sure you have balanced nutrients. It's sort of like the Redfield ratio for crops. You know, you have to apply the right ratios of nutrients to get efficient use of all of them. Such things as soil testing, online tools. I already showed you the crop sensors. They have some crop sensors that are lower tech that are more applicable to developing countries. Timing, it's amazing how much farmers in this country apply fertilizers in the fall, and then it sits there all winter long, leaching out, creating gases. It's for economic reasons and convenience reasons, but that could change, and it is changing. And then also, there are sophisticated ways of trying to get the fertilizer placed on the right place that would improve access by the growing plants. Well, remember I said that there are still about 800 million people who are malnourished, so it's not always a case of too much nitrogen. In many cases, such as sub-Saharan Africa, most farmers can't afford fertilizers and use practically none. And their yield, 1 ton per hectare, now I'm back in international units, SI units, is about 1/10 of the yield in Iowa farms. And it's been shown by increasing access to fertilizer and being able to use 50 kilograms per hectare, which is about 1/3 of what an Iowa farmer would use. They can increase their yield by about a factor of 3 to get up to about 1/3 of what an Iowa farmer would get. And furthermore, it increases their water use efficiency. The plants make more efficient use of water. And in many areas, like in eastern Africa, water is a growing concern, especially with climate change. And so there are some win-win situations here. Of course, people wonder, well, if you start using fertilizers in Africa and other parts of the developing world, are they just going to make the same mistakes that were used in the United States? Why not take a more organic approach? And all of the tools need to be on the table. But this research shows that looking at nitrous oxide as an indicator of loss of nitrogen, that yes, if you go to the same approach of using values, amounts that are similar to what would be used in U.S. agriculture or even Chinese agriculture, which is now often uses as much as 300 kilograms per hectare, you get very large nitrous oxide losses. But at this level here, at a 50 kilograms per hectare, they're very modest and still below the average IPCC, Intergovernmental Panel on Climate Change, emission factors for agriculture. As I said, there's no system that's 100% efficient. But it can be managed with minimal losses to the biosphere. Well, as I said at the beginning, more and more people want to have a better nourished diet, including choices to consume meat. And here are some examples, both in terms of total amount of animal protein consumption and also on a per capita basis. Projections into the future for both the US and Europe and China and India are big ones. Interestingly, however, while this is rather ominous increase, while there were predictions at this time when this particular report was published of continued per capita increase even in the United States, as well-nourished as we already are, a funny thing happened in that actually that has not come true. Now, I have to acknowledge that this is from the National Chicken Council, so it might be fake news. And when it talks about the fact that chicken consumption has gone up and beef consumption has gone down on a per capita basis, but overall per capita consumption has started to go down a little bit. Now, is this related to the economic downturn in 2008? Maybe, but it seems to have continued beyond then. Why is it? Maybe it has to do with economics. Chicken is very economical. Maybe the advertising campaign. You know, when I was a kid, chickens didn't have fingers. But now that's, you know, I think it's just a great a way of selling the stuff. And as a result, things are changing. And so the point is that human behavior does change. You know, 30 years ago, there'd probably be smoking in this room. I think it's a much bigger lift to try to get per capita meat production reduced. But human behavior does change. Now, this is an example of looking at dietary impacts on carbon footprint, but the nitrogen footprint is very, very similar since it's dominated by food. And when I give this talk, I have to say that, you know, I'm not suggesting that we all try to survive on oil, sweets, and condiments. I don't get invited back when I say that. And, you know, it's not that I'm trying to preach that everybody should be a vegetarian, although I certainly respect those decisions. But the main point here is to be cognizant of your dietary choices and that they really do make a difference. And that having some sort of combination of dietary sources and managing portion sizes can be very important. And in fact, now, if any of you are interested, you can go online and calculate your nitrogen footprint. In fact, this tool has been used at universities by undergraduates as part of classes to calculate the footprint of their university. And students in several universities have then worked with the grounds facility to examine their use of fertilizer for the lawns, with the food service to examine their sources of food and try to reduce food waste, with the heating system to try to reduce use of fossil fuels. And so students have taken this on and seen the impact, not only in terms of carbon and greenhouse gases, but in terms of nitrogen footprint, which I think is a great educational opportunity. So take note of this if you'd like to bring that back to your classes. Well, I'm going to hand the podium over to my colleague Xin Zhang now, who's going to talk more about some of the things that we can do to sort of galvanize the global community. And she's doing very novel work, I think, in looking at the sustainable development goals that have been adopted by countries throughout the world. Sustainable development goals both include sustainable agriculture, but they're also goals related to water quality and other aspects of sustainability. But we have such poor ways of measuring what is sustainable. Like equity, it's easier to say what isn't sustainable or isn't equitable than to say what is. But we think that we can use scientific approaches to come up with quantitative, albeit imperfect, indicators of sustainability. And that's what I'm going to ask Xin to talk about for the rest of this presentation. Xin.
Thank you, Eric, for the introduction. And so far, I think, so Eric has provided a great overview of the nitrogen challenges in the whole food system, and also discuss about a whole range of opportunities for us to address those challenges considering the whole food supply chain. So this figure's demonstrating or summarizing the nitrogen flows in the whole agriculture systems. And my talk or my story will be focusing on part of the agriculture system, namely this crop production. So this crop production section accounts for the majority of reactive nitrogen input into the agricultural system, and also accounts for the major nitrogen loss to the hydro system, such as water stream and estuaries, leading to environmental issues such as dead zones or eutrophication, which you all are familiar with. Just to take a closer look at the nitrogen budget in the crop production system. So the so nitrogen enter into the system through fertilization, biological nitrogen fixation, manure application, and the deposition. Among all those nitrogen input, part of them will be harvested as crop products. Some will be recycled or storage in the soil, and much of it, more than 50%, will be lost to the environment. Consequently, we can evaluate the efficiency of this system by calculating the nitrogen use efficiency as harvested nitrogen divided by the nitrogen input. And also calculate this nitrogen surplus, which is the difference between the nitrogen input and output, is also an indicator of the environmental impact of this agriculture, the crop production system on the environment. So in order to provide enough food for feeding the population while minimizing the nitrogen loss to the environment, improving nitrogen use efficiency has been proposed as one of the major strategies for achieving those two targets. But how has the nitrogen use efficiency been changing in the last several decades among the different countries around the world? So this figure shows two major efficiencies in the crop production. The x-axis shows the land use efficiency, in other words, crop yield, and y-axis shows the nitrogen use efficiency. And this gray color scales shows the nitrogen surplus, which is, as I said, is an indicator of the environmental impact of crop production. And the different color lines shows this 50-year trajectory of different countries around the world. As you can see here, all of the countries in the past 50 years has been moving to the left-hand side of the figure, searching for a higher yield. And meanwhile, most of the countries has been moving downwards, showing the decrease in the nitrogen use efficiency. Only a few countries, such as France and the US, has shown slight increase in the nitrogen use efficiency in recent years. So this declining or stagnant nitrogen use efficiency for lots of the countries around the world is actually contradictory to our intuition, because as Eric has discussed earlier, there has already been lots of the technologies and management practices has been proven to be effective in terms of improving how efficient crop plants can uptake nitrogen. And those technologies and management practices has become more available and affordable in a lot of countries, not only in the US or in France. So why we haven't seen a cross-border increase in the nitrogen use efficiency, and what are the reasons behind this apparent paradox in the nitrogen use efficiency? Probably some of you are familiar with this figure on the left-hand side. So this is a typical yield response function. It demonstrates that for a given farm and the management practices, as you adding more nitrogen fertilizer, your yield increase will start to level off. That's because as you having more nitrogen fertilizer applied, the other factors that limiting the crop yield become more important, such as water availability or soil quality. So corresponding to this diminishing return in this yield response, the nitrogen use efficiency would decline monotonically as you adding more nitrogen fertilizer. So the take-home message from these slides is that for a given farm and given technology, the nitrogen use efficiency is not a single number. Rather, it's affected. It can change largely according to how much of the fertilizer was actually applied. And the decision for the amount of fertilizer applied is largely affected by not only the environmental parameters, but also the socio-economic conditions, such as the price of fertilizer and crops, as well as farmers' attitude towards some risk factors. And for a farmer that operating based on under this baseline yield response function, there's the implementation of technologies and management practices can change this yield response in 3 different ways. The first type of technology can achieve the previous yield ceiling with a much less nitrogen input level. The example could be some of the precision farming approaches. The second type of technology can increase the crop yield, requiring similar or less nitrogen input. The example could be some of the control-released fertilizer. And the third type of technology can significantly increase your crop yield, but requires more nitrogen input. The example could be improved cultivars or some of the irrigation practices. So the point I want to make here is that all those type of technologies and management practices could be considered as more efficient because they can all reach the previous yield ceiling with a much less nitrogen input level. However, if a farmer operates at this black dot, would like to implement this pink technology, instead of operating at this triangle area, they would go up along this yield response function and search for the place that can optimize the profit. So as a result, instead of by implementing this pink technology, instead of reducing nitrogen fertilization rate, it's likely to increase the nitrogen application rate, and that may potentially result in the more nitrogen pollution, more nitrogen lost, as well as lower nitrogen use efficiency. So you might think, okay, it might make sense on a farm scale, but what does it mean for a broader scale? So let's just zoom out a little bit and look at what the nitrogen, the relationship between the nitrogen input and the yield level on a national scale. So this is a record of nitrogen fertilization rate and yield for corn production in the US in the last 50 years. And the slope of this red dashed line is determined by the fertilizer to crop price ratio. Based on those informations, you can actually estimate representative yield response functions. And that can help us to see how the technologies and management practices has been evolving in the last decades. So you can roughly divide them into 3 different periods. From the 61 to 71, the yield increase are mostly following the same yield response function, suggesting your yield increase are mostly achieved by adding more nitrogen fertilizer. From the 71 to year 2000, the yield increase has been achieved by going across the yield response functions, suggesting the yield increase has been mostly achieved by adopting the pink type of technology, which can increase the yield but likely to require more nitrogen input. From the 2000 to 2011, the yield increase are mostly achieved by adopting this blue type of technology or some of the red type of technology. So in the last 50 years, in contrast to the US trajectory, China has been following a very different path. So you can see this pink line shows a record from China, and it demonstrates, it's more in the last 50 years, especially for the recent 2 decades, the yield increase are more or less following this, the similar yield response function, suggesting the yield increase are mostly achieved by adding more nitrogen fertilizer or adopt some of the pink type of technology. And this has a lot to do with heavily subsidized fertilizer in China. And in fact, so this figure on the upper left corner shows the historical record of fertilizer to crop price ratio in different countries, such as US and China. And as you can see here, currently, the fertilizer to crop price ratio in China is about a quarter of the level in the US, providing very limited incentives for Chinese farmers to adopt more nitrogen-efficient technologies. But the factors, the technology and the socioeconomic factors that I have just discussed is only part of the reasons for the different nitrogen use efficiencies across different countries and along the timelines. So this figure shows a historical record of nitrogen use efficiency in China and the US. And it is true that China has lower nitrogen use efficiency than US for almost all types of crops. But even we can improve the nitrogen use efficiency in China to match the US level for every single crop types. This is how far that we can achieve. It only accounts for half of the difference between the nitrogen use efficiency between US and China. And the other half is caused by the very different crop mix that two countries has been producing. And the difference are mostly from two sides. One is US is producing a lot more soybeans than China. And soybean is a nitrogen fixing plant, is inherently more efficient in nitrogen use than a lot of other crop types. And secondly, China has been producing increasingly amount of fruits and vegetables. And when we look at the nitrogen use efficiency for fruits and vegetables across different countries, it's generally lower than many other crop types, especially the staple crop types. So this increase in the fruit and vegetable production in China is mostly driven by the increasing domestic demand, but it's also accelerated by some of the trade policies and agriculture policies. So this figure on the right shows the historical record of net fruit and vegetable import levels in US and China. So as you can see here, so this is from the year 2000. Like around the year 2000, the net export of fruit and vegetables increased significantly. when China joined the WTO, and also the government put forward some of the agricultural policies to encourage farmers to cultivate more cash crops, including fruit and vegetables. And it might be interesting to you here that for the U.S., the import of fruit and vegetables has increased significantly, especially after this NAFTA agreement passed. So it's actually, just from the national point of view, it might be a smart strategies to import some of the fruit and vegetables, and in other words, exporting some of the pollutions to Mexico. Anyway, so what does it mean for for us to achieve, or for us to meet the global food demand while bringing the nitrogen pollutions back to the planetary boundary? So there are many different ways to determine these targets, and I just use two commonly used targets to show you the directions that all the countries should move towards. And this vertical line shows the food production targets for 2050, and this curved line shows the planetary boundaries for the nitrogen pollutions from the agricultural productions. So in order to produce enough food to feed the world population while bringing the nitrogen pollution back to the planetary boundary, ideally, we need to bring all the countries to this upper right corner. So that suggests the increase of nitrogen use efficiency from a current 0.4 levels to a 0.7 level. And apparently it means very different challenges for different part of the world. For example, for countries like US and France, they're more or less moving towards this upper right corner, but as you can see here, there's still some distance for them to make, and this improvement in the nitrogen use efficiency need to be achieved by the promotion or the adoption of some of the nitrogen efficient technologies. And meanwhile, for countries like China and India, the challenge is how to halt this down spiral trend towards this increasingly serious nitrogen pollution by gradually phasing out some of the fertilizer subsidies and incentivize farmers to adopt more efficient technologies. And for countries such as for countries in sub-Saharan Africa, such as Malawi, the priority should be increase the crop yield. But the challenge is how we can increase the yield without following the historical trajectory of other countries and avoid this environmental coolness curves and achieve the higher yield while maintaining the nitrogen use efficiency. And that requires lots of the collaborations across countries and engage more technology transfer and capacity buildings in those countries. So some of the recent recently there has been another opportunities being proposed for improving the nitrogen use efficiency worldwide. And this is just a simple figure to illustrate such an opportunity. And x-axis is the nitrogen yield, y-axis is nitrogen input, and y-axis is crop yield. And for different countries and regions around the world, they locate at different yield response functions, or on the same yield response functions, but at the different stage. The key here is that by adding 1 unit of nitrogen, the yield increase could be very different. And the opportunity we have discussed earlier would be for a given country how we can shift this yield response by adopting more advanced technologies and improve ore management practices. And in addition to that, we can also consider from a global perspective that by reallocating some of the nitrogen resources to the places that can benefit the most from it, we can also meet the same crop production targets with much less nitrogen pollutions. Of course, you might think it's probably realistic for convincing Chinese farmers to apply less and use the same saved amount in African countries. But actually, such kind of reallocation of nitrogen resources and crop production has already been facilitated by the increasingly connected global trade networks. And this is just a kind of illustration of the major trade links for staple crop around the world. But this distanced consumption and production has also led to some of the unintended consequences. Unintended consequences such as deforestation and some of the systematic risk in the food supply system for the whole world. So that's make it very important for us to have a more comprehensive evaluation of the intensification strategies and to evaluate how the agricultural production affect the different aspect of the sustainability and the resilience of the global food supply system. So this is a project that Eric and I has recently developed. So this is sponsored by the National Social and Environment Synthesis Center, and we have coordinated a highly interdisciplinary group to lay out the plan for developing this sustainable agriculture matrix. So essentially, this matrix is trying to evaluate use a series of indicators to evaluate agriculture's impact from environment, social, and economic dimensions. And this is just a very early stage of the project. And the major goal for this project are mainly two aspects. One is provide a transparent and consistent measurements across different countries. And second, identify the social, economic, and ecological drivers for countries achieving sustainability in agricultural production. So this is just a very preliminary prototype of such a sustainable agriculture matrix. I just use the US as a example here. So the different colored shade shows the economic, social, and environmental dimensions. And under each dimension, you can have multiple indicators. And take the land use efficiency as an example. The different color dots shows the records from 1961 to 2014. And the dots that locates closer to the center means less sustainable, and the dots locates closer to the edge suggesting more sustainable. So it can demonstrate how the agriculture production being evolving in the U.S. In the environmental dimensions and the economic and social dimensions. And in addition to that, we can also engage the comparisons across different countries and helping us to identify the useful policy and the market drivers for achieving sustainability. And in addition to that, or more importantly, our data or matrix also have a crop-specific information, so that can enable us to identify or quantify the influence of crop mix in domestic production versus international trade. And this is just a quick example of for producing 1 unit of maize, how much of the environmental resources is required and what are the associated economic and social benefits. And this is the record for the US, China, Brazil, and Malawi. So the key point I want to make here is that for producing 1 unit of maize, it have a very different impact on the environment for different countries, and also bring in different economic and social benefits for different countries. And the difference is not only for one crops across different countries, but also happens for one countries across different crop types. Like for example, producing citrus fruit may bring in more economic benefits than maize and soybeans, but it might require more intensive groundwater use and nitrogen use. So based on those information, we can learn that in order to produce enough nutritious food for the global population, it really matters where to plant, how to plant, and what to plant. And with this tool, we can provide such an evaluation. So after all, I would like to summarize that or sustainable intensification can improve the nitrogen use efficiency, increase crop yield, and reduce nitrogen pollutions. The technology advance could help, and a lot of technologies has already been available and affordable. But social and economic impediments still need to be further investigated, and need to be overcome. So producing more food with low pollution will require integration among different disciplines and also cooperations across sectors. And this Sustainable Agriculture Matrix project would help the nations to gauge their progress towards the sustainability and modify their policies accordingly. And it really matters where to plant, how to plant, and what to plant. And of course, personal dietary choices matters a lot. So with that, I would like to thank the organizer for inviting us to be here, and would like to thank all of you to be here in the morning session. So yeah, with that, I would like to invite my co-presenters and answer any questions you might have.
Thank you for those great presentations, Pak Libert from UMSIS. I'm particularly interested in your projections for 2050 and the increased sustainability estimates. One of the factors that I didn't hear you talk about, but maybe you can comment as to whether it was taken into account. The fertilizer industry estimates that by 2050, nitrogen fertilizer production worldwide will be double what it is today. So how does that factor into your estimates?
So the targets that I talked about are derived based on the food demand and the planetary boundaries for nitrogen input into the Earth system. So that is not directly linked to the projections for fertilizer industry. I think their projections are mostly based on their growth curves for the fertilizer productions, and also probably considers the demand, the food demand, and the projected efficiency of nitrogen use.
And current fertilizer factories in production and construction.
Yeah, so, yeah.
I guess I would just add that all those projections, whether it's the population or nutrition or fertilizer demand, they're all based on a lot of assumptions. And so we try to bound those assumptions. And fertilizer efficiency could be increased, then the demand for fertilizer could be reduced.
Hello, Sarah Gouvet from INRS Quebec. I'm sorry for my English in advance. In your graphic showing the direction of the countries, it seems like you said that, for example, Malawi, to go in the same direction that US or France, it looks like you said that they need to produce more, right? Produce more, but more efficiency. But is it true that we already overproduce? Like, for example, in the US, the title of your presentation is Feeding 7 billion people, but maybe we already produced that, but the problem is the waste of food.
Yeah, food wastage has been estimated to be about a third. So there could be tremendous gains in efficiency by reducing food wastage. And they'll never be down to zero, but there are some reports or some targets of trying to get food wastage down to maybe 10%. And food wastage is very different in a place like sub-Saharan Africa. Most of it occurs before it gets to market. It either the fungus or rats or something consumes the food and the crops. That's the wastage, whereas in the developed world, it's on our plates where it gets thrown out. And so there's tremendous opportunities there. But any way you cut it, the people of Malawi or other sub-Saharan Africa want better food security. They want better economic security, and that means improving yield on farms. And so they are definitely underperforming. You could argue that we are overproducing internationally, but in any case, the Malawian farmer, the sub-Saharan African farmer, wants a better lifestyle, and that means producing more food per acre.
All right, one more.
Hi, Elizabeth Hilborn, US EPA. Excellent presentations, thank you very much. I was noticing in your graphics the nitrogen usage of nitrogen-fixing crops, such as the soybeans, compared to, say, maize. Is there a role for intercropping of these nitrogen-fixing crops with the crops that have higher nitrogen demand to reduce total nitrogen inputs?
Well, so I will try to address that. So we do account for nitrogen fixation as part of the nitrogen input into the agriculture system, and it is absolutely true that if you have, say, soybean and corn rotations, it can potentially increase the efficiency of nitrogen use for than the continuous corn system. So there are lots of the benefits for having this fixation, and fixing plants to be introduced, not only for the purpose of nitrogen use, but also will be beneficial for the soil quality or the soil organic matters improvement.
I guess my question was intercropping rather than rotation.
Intercropping, I see.
Yeah, there's a lot of experimentation with that in various parts of the world, agroforestry approaches, and I think that's one of the values of the sustainable agriculture matrix, is that it's simply presenting quantitative data for country by country, and it's up to each country then to figure out, well, we don't like our score on this particular matrix, this particular indicator. How can we improve it? And for a country like, say, Costa Rica, they might decide to experiment with some kinds of intercropping like you're talking about. In fact, they're already doing that. And that might be the way that they want to go. For the United States, we have a long history to overcome of not doing that. So I don't know how likely is to happen. We're just having a hard time getting farmers to use winter cover crops. And if we could get that far, we made a lot of progress in Maryland to get farmers to use winter cover crops, that would be a huge improvement. Intercropping would be another matter. I think it may be, in some cases, more likely to happen in tropical countries where it might be more feasible for a variety of biophysical and historical, social reasons.
Okay, let's give him a hand.